Okay, so first I'd like to thank the organizers for the opportunity to give this talk. Also, on behalf of the locals, thank you for bringing this nice workshop to Natal. And here's my plan for the talk. So first I'm going to start with some introduction about chiral spin liquids. Then I'm going to talk about a couple chain construction of a topological phase known as the Kalmar-Laughlin chiral spin liquid. On Monday, Chiral already talked about coupled wire constructions of topological phases. It's essentially the same idea here that I'm going to adapt to the context of spin chains. And then I'm going to move on to the main topic of this talk, which is the construction of a gapless phase from a cross-chain model. And even though this kind of coupled chain approach is an alternative to mean field like Parton constructions of spin liquids, at the end I'm going to show you that the result you get from coupling spin chains is equivalent to having a Parton construction where the spin is fractionalized into Majorana fermions in the bulk. And the first part here about the gap phase was done in collaboration with Ron Sella and Zvi Gorhovsky from Tel Aviv. The new stuff is in collaboration with Samuel Bieri from Zurich. So just to give a definition of a quantum spin liquid, we're going to talk about quantum spin liquids to refer to Mott insulators that do not break spin rotational symmetry in the ground state. So this is due to strong quantum fluctuations. And the interesting thing about quantum spin liquids is what they actually do. They have some exotic magnetic properties that stem from a spectrum of excitations that carry fractional quantum numbers. And these are called spinons. And according to this definition, the first spin liquid is actually a very simple system. It's the spin 1/2 Heisenberg chain. So this is the 1D chain with the antiferromagnetic exchange coupling J. And so it describes the spin 1/2s distributed on a one-dimensional lattice and just nearest neighbor coupling. And this model is actually integrable and exactly solvable by Bethe-Ansatz. So we know the exact ground state and the excited states. And we know, for instance, that the ground state, when you have an even number of spins, is a singlet, so it's unique, and it doesn't break spin rotational symmetry. Moreover, the exact excitations in the Bethe-Ansatz solution are organized as in terms of spinons. And there's a cartoon picture for spinons in one dimension. You can picture them as domain walls in some antiferromagnetic coupling, antiferromagnetic ordered chain like this, so that when you flip a spin, you actually break this excitation into a pair of domain walls that then are deconfined. They can move freely, independently of each other. The exact description is actually in the Bethe-Ansatz solution, and there we know, for instance, that if you calculate the spectrum of local operators, say the dynamical structure factor that are measured by neutron scattering, you actually, the excitations always create pairs of spinons, at least. And the experimental consequence of that is that if you do neutron scattering, instead of seeing a single coherent peak in the spectrum that corresponds to a magnum, you actually see a continuum of two spinon excitations. And this is the theory side, and this prediction has been confirmed by experiments and spin chain materials. So this is something we understand well. And then the next question is whether this picture of quantum spin liquids can be carried to higher dimensions, like 2 dimensions. This idea started with Anderson's resonating valence bond idea that you can actually construct a wave function in a spin system by a superposition of singlet pairs and assigning amplitudes for the singlets so that these amplitudes do not break any symmetry in the ground state. And then Anderson proposed that perhaps a wave function like this could be the ground state in a spin system that has frustration, where because you cannot satisfy all local interactions at the same time, perhaps the spin system chooses not to order, but to be in this quantum liquid state. And after Anderson's proposal, actually 30 years ago, Kalmar and Laughlin made this observation, this strong statement, that you can actually get an RVB-like state from a fractional quantum Hall wave function. The idea is that you can write down a representation for spin operators in terms of hardcore bosons, and then when these bosons move into dimensions, they will be strongly interacting, and they can move in the presence of an emergent gauge field, And what you could end up getting is actually a fractional quantum Hall state of these bosons at some particular filling factor if you have SU2 symmetry that is fixed to be nu equals 1/2. And this is the so-called Kolmar-Laughlin chiral spin liquid. It has all the properties that we know from the electronic fractional quantum Hall effect adapted to this context of magnetic excitations in a Mott insulator. So for instance, we know that this is a gapped state, so the excitations in the bulk are gapped. But if you put the system in an open geometry with a boundary, you find a chiral edge state, which in gapless chiral edge state, which in this case is charge neutral. Remember, this is a Mott insulator, but still the gapless edge state can carry spin and can carry energy, so there will be some experimental signatures as well. On the other hand, if you put the system on a closed geometry like a torus, you expect to observe topological order. So for instance, if you put it on a torus, you're guaranteed to have two-fold ground state degeneracy. And moreover, yeah, these two things are connected. Actually, the excitations that you get in the bulk of this chiral spin liquid, they carry spin 1/2. Like I said, they're going to be spinons. And they obey fractional statistics. They're actually abelian anyons that carry half of the statistical phase of a fermion, so they are semions. And yeah, like I said, this is very similar to a fractional quantum Hall state. So to get a chiral edge state like this, one thing that we should do for sure is to break time reversal symmetry in the ground state. But remember, this is a state that we describe that has SU2 symmetry, so the time reversal here is not broken by an external magnetic field like in a quantum Hall state. However, it can be broken in a different way that preserves SU2 symmetry. And the way to do it is that you can actually define this operator. It's a scalar, it's a triple product for take 3 spins on a triangular plaquette. You define this triple product. This was actually proposed as an order parameter for a chiral spin liquid when you have spontaneous breaking of time reversal symmetry. The interesting thing about this operator here is that it's odd under time reversal because it involves an odd number of spins, and it's also odd under reflections, which exchange, for instance, 2 and 3. So when this operator has a non-zero expectation value, it means that time reversal and inversion symmetries are broken. And you could define a chiral spin liquid as some state that has 0 expectation value of the spin operator. So it doesn't break spin rotational symmetry, but has a non-zero expectation value of the scalar spin chirality. So it breaks time reversal and inversion. And like I said, this was proposed about 30 years ago, and it turned out that the chiral spin liquid was not the ground state of, say, the Heisenberg model on the triangular lattice. Neither was the RVB state proposed by Anderson with that was time reversal invariance. But there was a revival of the interest in chiral spin liquids a few years ago, especially because of some numerical work that found chiral spin liquid ground state for relatively simple models. So, for instance, there was the work here by Bella Bowers, Montrevst, and collaborator. They looked at, with DMRG, exact diagonalization, they looked at this model that has, it's basically the Heisenberg model on the kagome lattice, but you add 3 spin interactions, so there's a J chi that couples directly to the order parameter of the chiral spin liquid. So in this case, in the Hamiltonian, you break time reversal symmetry by hand, but you still spontaneous breaking of time reversal symmetry is not actually essential for the chiral spin liquid. And they found that for a wide range of this ratio J chi over J, you get a chiral spin liquid. A gapped one, which is exactly the Kolmar-Laughlin chiral spin liquid. You can check that it has those properties that I mentioned. But also, it's possible to find chiral spin liquid in a model where the Hamiltonian is time reversal invariant, and this was done for the extended kagome lattice Heisenberg model. So you have the usual nearest neighbor Heisenberg coupling. You add second neighbor and third neighbor couplings. And here's the phase diagram that they found numerically. So in this region here, for sufficiently large J2 and J3, you find a chiral spin liquid phase. And notice that actually even for J2 and J3 equals 0, this point here, it says the pure Heisenberg model on the kagome lattice, you get a quantum spin liquid, but this is a Z2 quantum spin liquid that is time reversal invariant. Okay, so the question we are interested in here is whether you can start from that simple quantum spin liquid that we know well in one dimension, the Heisenberg spin chain, and pile up some Heisenberg chains and couple them in such a way that we get Kalmar-Laughlin chiral spin liquid. And before I describe how this works, I should mention that these couple wire constructions this idea has actually been applied to a large number of exotic phases, in various topological phases, and I'm going to tell you the story about chiral spin liquids, the spin liquid version of this. Okay, so we're going to start with a single Heisenberg chain. This is our starting point, and the good thing is that this is a well-known conformal field theory that has central charge C equals 1. This is the SU2 level 1 Weissman-Witten model. Here's the Hamiltonian. It describes the excitations of the spin chain in terms of collective modes. You can think that these are like spin bosonic collective modes that travel either to the right or to the left. They're described by these chiral SU2 currents here, J right and J left, and they travel with some velocity here, Vs. And these chiral currents appear, if you take the spin operator and take the continuum limit, the uniform part of the spin operator is just the sum of the chiral currents, and also there is a staggered component that defines here another field in the CFT. This is the staggered magnetization. And in addition, another operator that is important in the theory here is that if you look at S dot S for neighboring spins, the staggered part of that is what we call the dimerization operator. And all these guys, the J's, N, and epsilon, they actually form a closed algebra under operator product expansions in the CFT. And this is all known. They can all be represented in non-abelian bosonizations in terms of a single matrix field. So this is something we can use here. So let's now take two Heisenberg chains. Right? Start simple, and we're going to couple them in such a way that afterwards we want to add these three spin interactions that induces the chiral spin liquid. So because of this, I start couple them with some triangular geometry like this, and this is known as the zigzag chain. So what we have here is some coupling J along the legs of the chains, and between the chains there's this interchain exchange coupling J prime. Here I'm separating the chains such that chain 1 contains the odd sites and chain 2 contains the even sites, so that's why it's labeled like that. And this zigzag chain was studied a lot back in the 90s, so we know the exact phase diagram. For us, the interesting limit is when this J along the chain is much larger than the interchain coupling J prime, and it's known that in this case, here the ratio J over J prime is very large. You're inside a gap phase, which is dimerized, or it's a valence bond crystal. And in this case, the ground state is actually fully gapped, but this phase is topologically trivial. The ground state is twofold degenerate, but because it breaks a discrete translational symmetry. To get something different, now we're going to add three spin interactions to this model, like the one in the work by Bella and collaborators. So we add the J chi that couples to the order parameter of the chiral spin liquid, and choose the chirality here in the triangles of the zigzag chain. And we have to choose the orientation of the chirality here. I'm going to choose it so that the chirality is uniform. It's the same sense of rotations in all triangles. This fixes the order of the spin operators in the triple product. And then you can treat this J prime, the exchange coupling, and the J chi, the three spin coupling, as perturbations of the Hamiltonian of two decoupled chains. you go to the CFT and ask what kind of operators you generate from the operator product expansion, taking the continuum limit. So if you only have J prime, it's known that this interchain coupling generates some current coupling between, say, right movers that live in chain 2 and left movers in chain 1, and vice versa. And this coupling is time reversal symmetric, as expected. This is just the usual exchange. But if you now do the same thing for the time reversal odd operator, there is the 3-spin interaction, you also generate J.J couplings between, say, right movers on chain 2 and left movers in chain 1. But now this thing has to be odd under time reversal and odd under inversion. And both transformations here exchange right and left. You can check that the way this works is that you actually get a minus here. So it's different from the combination that we have up there. So it's essentially the same operator but with different sign. You can now add these two things. And what you get is are these two combinations. Yeah, so you have coupling between two on chain 2 right movers, on chain 1 left movers, with an amplitude here that is different from the amplitude for the other pair of chiral bosons. And the interesting regime is that when this chi that you get from the 3-spin interaction, these are dimensionless coupling constants, by the way. When chi is larger than G, what you get is that this coupling constant is positive and this one is negative. This is important because these are marginal operators, so we know that whether they're marginally relevant or irrelevant depends on the sign of the coupling constant. And in this regime, this one here is going to be relevant. It's going to flow to strong coupling at low energies, which means that the pair of chiral currents that are coupled by this operator, they're going to be strongly coupled and gapped out of the system. This is the pair where you had right movers here on chain 2 and left movers on chain 1. So these guys are gapped out at low energies. On the other hand, for the other pair, this coupling constant is negative, and then it flows to weak coupling, which means that this pair of chiral bosons is left gapless in the low energy limit. So this means that in this picture here, you have gapless right movers on chain 1 and gapless left movers on chain 2. And then you just generalize this picture to n lags, so you couple n spin chains, skipping all the details. Basically, the idea is that you start gapping out these pairs of right and left movers that live in neighboring chains, but at the end, you're left with a right mover that propagates on the lower chain, on this boundary, and a left mover that propagates along the last chain, so on the other boundary. This picture here describes a system that is gapped in the bulk, but has gapless edge states. This is precisely the Kalmar-Laughlin chiral spin liquid that I described before, because it has chiral edge states, which are now described by an SU2 invariant conformal field theory. That's a chiral Weisman-Witten model, just for right movers on this boundary. Also, the bulk is gapped, and the way you can see this is that when that operator that couples pairs of right and left movers in neighboring chains flows to strong coupling, you can go back to abelian bosonization and pin the bosonic fields that live in neighboring chains to a particular combination. So this pair here of bosons is gapped out, and the excitations would correspond to phase slips of this combination here, when this combination changes by 2 pi. And the excitations that do this, you can ask what are the quantum numbers that they carry, and you can check these are actually, these excitations carry spin on half. So this is a gap phase where the excitations are spin on half particles. These are the gapped spinons of the Kalmar-Laughlin chiral spin liquid. And moreover, you can actually describe write down the operators that creates these kinks in the phase, that creates quasi-particles, and you can either change the spin by +1/2 or -1/2, and there are these two operators written in terms of the bosons. These are actually the two components of the chiral spin of the Weisman-Witten model, something that is also known in the CFT. It's the bulk, yeah. So these guys are, yes, here. Okay, and you can also check that you can recover other properties that I listed before, like topological ground state degeneracy, and so on. Let me just point out that the same construction can be generalized if you now replace the Heisenberg chain by other kinds of spin chains that have other conformal field theories. For example, you can generalize it to SU2 level K, West-Wheaton models, and get even non-abelian chiral spin liquids. So for instance, it's known that if you take the spin 1 chain, it has a phase transition between a Haldane phase and a dimerized Alveolus von crystal phase. Here at a critical point E equals 1. This transition here is described by SU2 level 2 as a Wheaton model, which has central charge C equals 3 halves. And you can then, you should then expect that if you start coupling these spin 1 chains, fine-tuned to this critical point, you couple them with 3 spin interactions. Up here somewhere, you should get a 2-dimensional phase that is just the non-abelian version of what I described before. You can check that, you can write C equals 3 halves as one boson plus 1 Majorana fermion, and show that the kinks in the phase of the bosonic mode will trap Majorana 0 modes. Yeah, but as far as I know, this has not been done numerically yet. So you have the state degeneracy associated with topological order, but here the idea is that if you now start creating quasi-particles, then you have the degeneracy associated with these non-abelian anions, non-abelian spin nodes in this case. Yeah. Okay, so let me now move on to the main question then. So what about the gapless spin liquid? From what I've described so far, it's not very clear how or whether we can get a chiral spin liquid from this kind of coupled chain construction, because the way this construction works is that you take the parallel chains and start gapping out modes in the bulk, and you're left only with gapless modes at the boundary. So how can you get gapless modes in the bulk? And also, it's not clear why we should look for this. Why do we believe it exists? If you only have 2 legs, it's not possible really. That's like the quasi 1D version, like of what the. Yes, so you couple large number of chains, then you can talk about bulk and boundary. But the idea is that the seed of the chiral spin liquid was already contained in 2 legs, and you just have to generalize it to an arbitrary number of legs to get the 2-dimensional phase. Okay, so what about this gapless phase? So one motivation to look for this is that it has actually been seen numerically. This was the same work by Bauer and collaborators that I mentioned before, where they found the Kalmar-Laughlin chiral spin liquid. The gap phase corresponded to taking the kagome lattice and having uniform chirality, this 3-spin interaction, on all small triangles of the kagome lattice. What they found is that if you actually stagger the chirality between nearest neighbor triangles, so the blue and green color here represent the chirality is opposite in these triangles, they found a gapless phase, or evidence for a gapless phase from a 2-leg ladder. And so, yeah, this is what's shown here. This is a finite size gap, scaling to 0 as you increase the system size. And they had this intuitive picture for how these gapless modes could survive by like reconnecting the chiral modes inside the bulk. What I'd like to do here is see how this picture can emerge from some analytic coupled chain approach. Another motivation for thinking about this is, that's actually how we came back to this problem, is this question about maybe this gapless chiral spin liquid exists in nature. And there was actually this material called capellasite. This is like a cousin of Herbert smithite. It's also a kagome system. The magnetic ions here are copper 2+ that form a kagome lattice. But the interesting thing, peculiar thing about the system is that because of the exchange paths, you have all these different exchange couplings. J1 is the usual nearest neighbor one. There's J2, and there's also a JD. D here stands for diagonal. It's the coupling along the diagonals of the hexagons in the kagome lattice. J3 is not going to be very important, but the main point here is that these coupling constants have been estimated from high temperature expansions for the specific heat and susceptibility compared with the experiments on this material. And the strongest coupling is actually this further distance one, JD, along the diagonal. And it's antiferromagnetic, whereas the other ones are ferromagnetic. That's because of 90-degree bond angles in this geometry. And people have done measure specific heat and susceptibility. There are some neutron results that kind of suggested that there was no phase transition to a magnetically ordered phase in this material, so people started speculating about whether it could be a spin liquid, and then in this paper here, they proposed that maybe capelasite is a Chiral spin liquid with some fermionic spinons, and this was based on variational Monte Carlo calculations for this model. No, JD is only along the diagonals of the hexagon. So here it's the same distance, but JD is going to be restricted to the diagonal. And this OJ3, the value is negligible. It's much smaller than the other ones. So I'm actually I'm not going to talk about J3 anymore. So here's again the kagome lattice. If you look at the vertices of the crossings of these dashed lines, those would be the sides of the kagome lattice. But I want to point out that this model where J diagonal is much stronger than the other couplings is actually gives us a good starting point for treating this problem as cross the spin chains. So take one particular side of the kagome lattice. So if JD is the strongest coupling, this side here is more strongly coupled to its neighbors here across the diagonal. So this side now belongs to a spin chain along this direction. And the same is true, say if you take this side, then there is another spin chain that runs here. If you take now a different side on the first hexagon, say this one, there are spin chains running this way and spin chains running this way. So you can see that there are 3 sets of parallel chains that form 120 degrees, 20 degrees angles. And in the next slide, I'm going to actually label all the spin operators on this lattice like this. So there is an index Q that labels the color here, or the direction of the spin chain, 1, 2, 3. X is the position along a given chain, as usual, and Y labels different parallel chains in the transverse direction. And these positions are actually not Cartesian coordinates on the two-dimensional plane. They're labeled in a way that takes advantage of the C3 rotational symmetry, right? So it's just illustrated here. I'm just saying this because in the next slides, if you see some strange coordinates, it's because the sides are labeled like this. Okay, so yeah, so that was one motivation that the model for capelasite could maybe stabilize a Chiral spin liquid state. But later there was this paper by Gong and collaborators where they did some perturbative randomization group analysis and also DMRG on cylinders, and they concluded that there's actually no Chiral spin liquid in this model that I described to you. And this is the phase diagram they get from DMRG. So here, so JD would be the strongest coupling, and these are J1 and J2, the ratios to JD. So first of all, if J2 is much stronger than J1, you get a magnetically ordered phase that is called the Kubock-1 phase. This name comes from the fact that if you look at the way, this is a classical phase where the spins are ordered in different directions. It has a large unit cell. If you take all the vectors in which the spins are ordered, there are 12 of them, and you place them at the same origin, this picture here defines a Kubock dihedral. Okay? That's why it's called Kubock-1. There's another classical phase, order phase, where we also define a cube octahedron, but in a different pattern. That's the cube octu phase that appears in the regime where J1 is the strongest as compared to J2. And I should say that both cube oct1 and cube oct2 phases are actually chiral in the sense that they have a non-zero expectation value for the scalar spin chirality, because this is a non-coplanar order. However, it's not a chiral spin liquid because this breaks spin rotational symmetry. And the hope to find a chiral spin liquid was that maybe it would appear at the boundary between these two ordered phases when the both kinds of orders melt, so you lose the long-range magnetic order, but you could still preserve the scalar spin, non-zero expectation value for the scalar spin chirality. So the hope was that the chiral spin liquid would be here. These guys concluded that what you actually get inside this region is a valence bond crystal with a large unit cell. And by the way, this red star here is the model for the parameters for capellocyte. So it seems that actually all the evidence suggests capellocyte is inside an ordered phase, and the fact that we don't see a phase transition probably has to do with disorder. Still, I'm going to take this model for capellocyte as a starting point for constructing the chiral spin liquid. Well, if you add the right kind of staggered chirality to the Hamiltonian. So let us now add something here, like in the same idea that we used for the Kalmar-Laughlin chiral spin liquid. We're going to add 3 spin interactions to the right triangles. So our first guess, which seems the most natural one, is that maybe what we should add is some staggered chirality to the small triangles on this lattice. But it turns out that if you're approaching this from spin chains, this does not work, for the reason that on these small triangles, these 3 sides have different colors, which means they belong to different spin chains. And what you get in the effective field theory for weakly coupled chain is a product of 3 currents in different chains. This is an irrelevant operator, so it's not going to drive a new instability on the phases that we already know. So remember that what we wanted from the Kalmar-Laughlin chiral spin liquid was a kind of J.J or 2 current coupling that could be marginally relevant and drive us to the chiral spin liquid. So because of that, the criterion here for choosing the chirality on the triangles is that we actually want to pick triangles where 2 sides belong to the same chain. So if you take a pair of sides like this, so there are 4 triangles of this type, and you choose the orientation of the chirality so that you generate these J.J couplings to lowest order in J chi, the coupling constant in the lattice model. And by hand, yes, breaking time reversal symmetry by hand. And yeah, so this is the criterion, and this gives this particular pattern for the chirality. It's important to note here that this, like I just said, breaks time reversal symmetry because we have 3 spin interactions. It also breaks a reflection symmetry about this vertical line here called sigma prime, because this would reverse the sign of the chirality, but it preserves a reflection symmetry about a line that is parallel to the spin chains. This is sigma here. And it also breaks the C6 rotational symmetry of the kagome lattice down to C3. So we're going to do here is now analyze the effects of this perturbation within a perturbative randomization group analysis. Just one technical remark, that in the usual cases when you're doing randomization group in 1 dimension, you have to define some sort of ultraviolet cutoff, which can be short distance cutoff alpha, and then you grow this cutoff, which means that you're looking at correlations at larger and larger distances. Here in this particular problem, we actually have this issue that as you grow this short distance cutoff alpha, you actually grow the region where this chain crosses other chains that are running in a different direction. This means that when you're growing alpha, you actually have to allow for the fact that these parallel chains in the other directions within this region here are not distinguishable. They're actually going to be correlated because they're crossing the same chain. In practice, what this means is that when we calculate correlation functions or use the operator product expansions, I'm going to allow here for the fact that in the transverse direction, there is a broad and delta function that correlates chains when they're with a distance alpha, within a distance alpha. And this could be any short distance correlation. We take a caution in practice. And with this prescription, we can analyze what happens. And basically, the story here is that you can derive a ground state phase diagram by looking at the dominant instabilities. And here we find that for sufficiently large chiral coupling JK, you stabilize a chiral spin liquid, which happens when this particular interaction here reaches a strong coupling first. You look at what that interaction does. I'm already labeled this chiral spin liquid. And what happens when it flows to strong coupling. Now, this was an interaction that we didn't have before, where it didn't flow in the case of parallel chains. This is the interaction that couples only right movers. So when this guy flows to strong coupling, it gaps out all the right movers in all the chains at the same time, but leaves out gapless left movers in the bulk. So the picture would be something like this now. There you have these coarse grain chains where you allow correlations at some finite distance that have only chiral movers, left movers propagating them as gapless modes, whereas the right movers are gapped with some gap that depends on the scale where this coupling constant reached strong coupling. And beyond this distance, what you get is that you can show that perturbations of this decoupled chain Hamiltonian are all irrelevant, and this is actually an instance of what has been called a sliding Luttinger liquid in the literature, a system of decoupled Luttinger liquids. When in this case it's chiral because it only has one chiral mode in each thing. It's gapless, so it depends what you mean, but it has spinons, so it's say it's non-trivial. Yeah. And you can check some properties of this gapless chiral spin liquid. So, for instance, sliding the name comes from the original sliding Luttinger liquid, which was some kind of semantic phase where you actually could, with the fact that you have decoupled Luttinger liquids, you could slide the charge of one chain with respect to the other. That's right. They're uncorrelated at large distances. Okay, so we can calculate spin-spin correlations and show that the decay has power loss, whereas correlations of the other fields that involve the gap modes will decay exponentially. You can calculate the entanglement entropy for this phase, and it comes from just a simple counting that if you take the Cardi-Calabrese formula in 1D, and in the picture that our system is actually a bunch of crossed decoupled spin chains, you count the number of chains that cross the boundary of system, and then this number scales with L, you get this dependence that the entanglement entropy goes with L log L, which is actually the behavior that people have found for free fermions in 2 dimensions, but can be extended to strongly correlated systems that can be viewed as a large number of chiral 1-dimensional modes. Can also show that this is a gapless phase, but it's robust against disorder, has vanishing thermal Hall response. And then I'm running out of time, but maybe just point out at the end that all these properties that we got from this coupled chain construction are consistent with a Parton construction, a la Kitaev, where you fractionalize the spin operator like this. This has a Z2 gauge structure, so you have to impose a constraint. And if you do a mean field decoupling of this theory with 3 Majorana fermions hopping on the lattice with the same kinds of couplings that we had on the extended kagome geometry, there are some symmetry constraints. If you impose the symmetries that I described on this tight binding model for Hamiltonians, you can get this tight binding model, you diagonalize it, and you can actually show that the spin correlation you predict from this model is actually a square of a Green's function of a Majorana fermion. And it has, even though this is a two-dimensional face with now a 2D Fermi surface, the Fermi surface is aligned, and then because of this, it has 1D-like correlation. So instead of 1 over r cubed in 2 dimensions, you get 1 over r squared for the 1D correlation, for the spin-spin correlation. And this was actually seen before, or pointed out in a different context, so a model of a quantum spin liquid with Majorana fermion excitations on the triangular lattice. It turns out that it also has these highly directional correlations where you have the correlations are non-zero only along special lines. They form 60 degrees, and then it decays exactly as 1 over r squared, even though you're taking a two-dimensional tight binding model. And with that, I will conclude with this, and thank you for your attention.
All right, thank you. Questions?